Thank you. It's an honor to be here. I'm going to tell you about learning, which I don't think is passé, and how learning, and specifically how computer learning, can help improve all of our lives. So for many years, people said, what does it mean that computers can learn? Computers can only do what they're programmed to do. So let me first try to convince you that computers can learn and tell you a little bit about how that's done. So a computer system takes an input and does something with it and produces an output. But all programs have a certain set of parameters that dictate how the program works. And those parameters are something that we can learn and adapt in order to get a better input-output mapping from the computer program. So computers can learn to make good predictions. Computers can also learn to act in the world in order to improve their behavior. Now, there's many applications of machine learning that I could have told you about, and version 0 of this talk had a lot more of them, but it went on for about an hour and 15 minutes, so I had to cut a lot of them. So speech recognition, fraud detection, intrusion detection, processing of images and videos, autonomous driving, as in DARPA's Grand Challenge winner used a lot of machine learning, a lot of medical applications, some of which I will talk about, and some basic science applications, which I'll also briefly mention. So I don't have time to go into all of these, so I'm just going to give you a few highlights to illustrate the many uses of this technology in a whole range of different applications. I'm going to start with a simple example, but yet one of significant importance. We have all had to deal with spam email cluttering up our mailbox. I think not many of us realize just how big this problem is because spam filters currently get a lot of those emails, but it currently comprises about 90% of email traffic. And a fairly conservative estimate a couple years ago says had that this costs US organizations, and that's just in the US, over $13 billion a year. Worldwide, of course, the cost is much higher. Now, one of the problems here is that it's a moving target. Everything that we do in order to prevent spam, spammers adapt in order to circumvent those. And so any hand-constructed system just doesn't work. It just fails pretty early in the process. So how do you use machine learning in order to do spam better? Well, detect spam. So here is an example that I picked out of my spam filter just for this talk. So I just opened my spam filter. This was one of the first ones there. And so how do you deter it? And fortunately, my spam filter did catch that. How does one detect that this is spam? Well, so a typical spam filter will look and see what words exist in that message, and it'll notice words like pharmacy and phrases like unique offer and multiple exclamation marks. And then the spam filter has a set of parameters, which in this case tell us how important these words are in terms of indicating spamness. So for instance, pharmacy is a pretty good indicator of spamness. Unique offer is an even better indicator of spamness. Doctor, maybe a little bit. Exclamation marks are pretty good. And so you take those, you put them together in some sophisticated way that depends really on the exact algorithm that one uses, and out comes a number that says the spamness of this email is 18.3, at which point one can determine a threshold of your false positive versus your false negative and determine whether you want to screen this particular message or not. And it is those parameters that are learned by a machine learning algorithm to optimize your ability to detect spam. And basically, you want to increase the parameters for words that tend to appear in spam email and decrease the parameters for words that appear in good email. Now, learning here occurs at many different places. Most spam filters have a bit of learning that they do in advance, but most of the learning actually happens using a process called online learning, which adapts to what the spammers are currently doing. They also adapt to personalize relative to people's own preferences. Some people might want to get Viagra ads. I don't, but some people might. And so there's a personal adaptation, and there's also collaborative learning that goes on, which is another new technology whereby people learn from other people's preferences. Now, this is a fairly simple application, which is why I used it to explain the technology. Let me show a few harder ones. So machine translation came up earlier in in a few of the other talks. Machine translation is another text processing application, but it's a lot harder. The input can no longer be viewed as a bag of unrelated words. It actually needs to be viewed as a coherent piece of text. The output is not a binary yes-no decision, but a complex sentence that also needs to make sense. And there were many efforts to try and do machine translation using hand-constructed, linguistically based translation rules. And one of those systems, this is an apocryphal tale from a number of years ago, came up in around the time that people were trying to build English to Russian translation systems. This was right after the Sputnik launch, which caused a lot of US scientists to want to read papers in Russian. And so this is one of the translations that one got from going from English to Russian and back again, which, as you can see, leaves something to be desired. So, machine learning-based systems use an enormous amount of text in two different ways. First of all, they use what are called match corpora, text in two different languages, to learn how words or phrases in one language map to words or phrases in the other. Now, you could get that from a dictionary, but again, there's so much of it and usage changes so often that doing this from learning is a much more robust way to go. Second, they use text in a target language to learn what good text looks like so that one can produce sentences in the target language that actually make sense. And uses these two learned components, puts them together to get the performance that we have heard about in the previous talks, which is certainly far from perfect, but is very, very usable, to the extent that, as we heard in Alfred's talk, there's now 40 languages that one can that one can translate between. A very different application where hand-constructed systems simply did not work for decades is perception. And let me take as a very simple example, again, automated handwriting recognition, which you might think is easy until you see the variety of ways, that people write even a simple digit such as the word 9, such as the digit 9, and you try and think about how to explain to a computer that this is in fact a 9 and what makes that different from other things. And it is very hard to do that. It's even harder when what you have is a much more complicated text consisting of letters and digits written in arbitrary locations on, say, a piece of mail. And yet, there is currently an automated handwriting recognition system that is deployed at every single postal distribution center in the US. It processes over 25 billion letters annually. 92% of them are processed automatically, saving the US taxpayer hundreds of millions of dollars every year. And this is purely a machine learning-based system. Now, this is a very, in some sense, a simple perception problem. There's only one sensor. You have to read a piece of paper. A much more complicated example that, again, is a fielded application is learning to figure out what our traffic looks like. Here, there is heterogeneous sensors. You get multiple views of traffic. You get weather reports. You get incident reports. You get information from those little sensors on the highways. And you'd like to put that into a learned program. And what does the program learn? It trains on historical data, and it learns to predict two things. It learns to predict the current road speed on roads that aren't sensed right now, like, for instance, surface streets that are adjacent to freeways, and also learns to predict future traffic conditions, like what's traffic going to be like when you hit that traffic jam in a half an hour. And so what you get is a roadmap that gives you green and red and yellow sensors, but that don't only correspond to the sensed highways, but to every road that you might want to take. And it does dynamic route optimization, tell you how to get to your destination faster. In an experiment that was done at the I-95 corridor, which is something that I think resonates with a lot of people in this room, this system was discovered to be accurate to about 5 miles per hour in a vast majority of cases, and it's currently fielded in 72 cities. A very different example, again, I'm picking vignettes from different application areas, is controlling or acting in a complex system. So here's a little robot. It's a little toy dog, and this is what the toy dog does before you train it. This is the original code provided by the manufacturer, and it didn't work very well. And after machine learning, the robot learns to navigate very complicated terrain. And it also learns to do things the manufacturer never intended it to do. Now, this is one example. Here's a very different one. This is flying a remote-controlled helicopter, which is one of the most challenging tasks, even in a human pilot, upside down. It does loops. It does pirouettes. And it does a maneuver called as chaos. These are challenge maneuvers from an aerodynamic show. And this is a purely learned system where the robot learned to do this behavior by itself. And how does it learn this? It learns in two ways. First, it learns in an apprenticeship mode, much as a human pilot would learn, by emulating a human pilot and seeing how they respond to different situations. But then, equally importantly, it learns by doing. It learns by adapting to its own experience, adjusting the parameters inside this program to reward behaviors that keep it stable, that prevent it from crashing, and that allow it to execute the maneuvers. This is not just useful for automated vehicles, although that's an application that by itself has significant merit and importance. Here's another application where one could use this. This is an application that currently is starting to be explored. We've all heard about the difficulties with a power grid, where the key problem is that energy is produced in one place at one time and used in a completely different place. And so how do we move it on the limited infrastructure to where it needs to go? The importance of this is not to be underestimated. I think all of us remember in 2006 what happens when the entire eastern seaboard went dark, giving rise to a picture that looks like this. That was a failure in the control system. One line went down, but that wasn't the problem. The problem was that that all the electricity was therefore shunted on other lines that were simply incapable of handling the load, and that's what caused the entire system to blow. A smart control system would not have done that. And so the solution is learning, and it combines both the perception aspect that I mentioned, where one predicts both the current and the future demands, as well as building robust and efficient controllers. The final thing I'm going to talk about is medical and scientific applications. So one application that has been demonstrated as being outperforming even expert humans is diagnosis, where it's been demonstrated that a computer diagnosis system outperforms most physicians and is at a par with expert physicians. And that's a very important thing in terms of allowing, say, triage by less experienced people. So for example, a parent who's concerned about a sick child in the middle of the night can log into a system, and the system asks it intelligent questions about the symptoms of the child in order to help provide a more useful diagnosis in terms of what to do in the middle of the night. Other systems that also would be that are also really that are more modern, that are currently evolving, but would be equally useful. Here is a patient-specific. Here's a system that, on a patient-by-patient basis, detects epileptic seizures from EEG data and intervenes at the patient in real time by electrical stimulation to reduce the severity of the seizure. So here it's a very complicated signal. This is what the signal looks like, and you're supposed to take that and predict from that when the seizure begins. And basically, here's a list, here's a set of patients that this was tried on. This is the latency for detecting the seizure for generic approach, and this is the per patient learned model, and you can see that it detects the seizures not only more often, which is a graph that I didn't show you, but also with a much lower latency. There's all sorts of other applications, reducing the frequency of medical errors, which are costing enormous amounts both financially and in human life. You can learn the standard of care. What do you do for given patients for different types of problems? And then detect anomalies, which are cases when those protocols weren't followed. You can use home-based systems for tracking of chronic patients, diabetic patients, for example, for early prediction of complications, reducing both pain and suffering and the cost of unnecessary hospitalizations. Finally, and we'll hear a lot about this from Gene Myers in a little bit, I think, about how new technologies revolutionized biology. These include high-throughput sequencing, gene expression measurements, protein-protein interactions, and many more. But a real question is, what do we do with this flood of data in terms of understanding and curing disease? So let me show you a little bit about some work that's been done in machine learning along that front. All of us are actually very similar to each other in terms of our DNA. Only 1 in 1,000 of the letters that determine our DNA differ between us. But these differences determine who we are, what we look like, what we like, but more importantly, what diseases we'll get and which medicines will work for us. So you can look, for example, at the DNA of diabetic patients and healthy individuals, and you'll see that there's a lot of these little differences, but only a very few of them matter. So how do you detect what matters? Which of these changes make a difference? So the first thing you have to figure out is, where are the genes? Now, only 5% of the DNA appears to play a functional role. How do you find that 5% that is significant and that corresponds to genes? So that's something a person simply can't do. But you can give a computer system a set of examples of known genes. You can learn what characterizes DNA sequences that start a gene or end a gene or are in the middle of a gene. And this is the performance of gene detection systems over the last decade, starting at 10% of human genes detected, and currently we're at about 50, and the curve continues to rise. There's a lot of places where one can go with this. And I think the most exciting direction, and one that I'm personally very interested in, is there's been a lot of talk about evidence-based medicine. Figure out what works. Well, what works is not the right question, because what works for me might not be the same as what works for Peter, because each of us is different and we're going to respond to a different set of drugs. And so what I'd really like to know is not what works, but what works for me. And with electronic medical records and the growing availability of DNA data at a personal level, we can now learn a mapping from individual genotype and other environmental factors to things like disease risk and drug suitability, which would allow us to personalize the treatment to individual patients, getting much better healthcare for everyone at a much lower cost. So just to summarize, machine learning is a little bit like steroids or illegal. Anytime you have a challenging application, if you look around, you'll see that there's usually, especially nowadays, a lot of data that can speak to the application and can help us do it better. And so we can take that data, we can apply machine learning technology to make that application better. And this is a core technology. It can be used for a broad range of applications. It can be used for cases where other hand-engineered methods simply don't work, like perception, personalization, or adapting dynamically to a changing situation. And it can basically improve almost any application that you're interested in dealing with. And a little bit of learning will go a long way. Thank you.